This final talk brings together our three components of population change: fertility, mortality and migration, and describes how we use these to produce a population projection using what's known as the cohort-component methodology. So we have a really strong link here to the subsequent training materials that are also provided as part of this project on POP Group, since POP Group uses the same cohort component methodology to produce its projections. In the exercise that's connected to this talk, you will produce a population projection using the cohort component methodology by hand. And this is really a set of processes and calculations that POP Group automates. So as we can see from this quote underneath the population projections title, population projections have a long history of being used for planning purposes. So a long history of planners developing estimates of how the population will change in order to provide services for populations living within areas. We also require projections to produce estimates of the current population for time points where this is not known directly. So this involves a process of going back to when we last did know the population accurately, or we accurately count that. So for example, this might be the last census, and projecting that last reliable point of data we have at the census forwards to the present by adding in our estimates of births, deaths and migration. This is a methodology that National Records of Scotland and other national statistical agencies use to produce what are known as the mid-year population estimates. To estimate the population for a future time point, we have a distinction between this approach of estimating the current population, in that here we have to make assumptions about births, deaths and migration. We don't have direct data estimates on these things. We need to make a prediction about how they will change in the future. So forecasts or predictions are projections of the future population in which the assumptions are claimed to be likely outcomes. So here's a diagram indicating some of the points I'm making here. So we have a reliable estimate of the population at a census, and then in the intercensal period we need to update those census estimates based on estimates of birth, deaths and migration that we have to generate mid-year population estimates. When we're going into the future, we need to make projections of how those components of change, births, deaths and migration, will change in the future. And we can use the past to inform that. So I talked about the importance of population estimates and forecasts. This is one of the most important areas of applied demography, and there's a real large demand for both national and subnational population counts by age, sex and other demographic details. So this might be used for monitoring social trends. So if we're interested in how unemployment is changing over time, or how indicators of health are changing over time, we typically need a population denominator capturing the population at risk of those particular events in order to see how rates of employment and so on change over time. We need population estimates and projections to distribute resources from national to local government, and we need to know about how areas are growing or declining in population to inform that distribution. We might use these demographic estimates in investment of new resources, so providing the statistical backing for grants and loans around particular projects that might respond to population change or change in population age structure in particular places. Or we might want to use these estimates and forecasts to assess the present and future demand for services, for houses, for pensions and so on. And in the private sector, we can see that this kind of information is crucial for business marketing, for deciding the size and the characteristics of catchment populations to inform the geographical locations of stores and so on. So the cohort component method of population projection is represented by this basic demographic equation of population change, in that if we are interested in the population at time t+1, we take the population in our base year t, we add on any births that occur, we take away any deaths that occur during time t, we add in migration, and we take away out migration to give our population at time t+1. So we're essentially taking the population size and age structure for a known start point. We're aging that population on after taking into account additional births, taking away deaths, adding in migration, and subtracting out migrants. So we can use this method in two ways. We can use it to update census estimates to produce an estimate of the current population. And we can also, by making assumptions about the future, project what the population will be like at a future point in time. So this slide illustrates the difference between using a population projection approach to produce an estimate versus making a prediction about the future. And crucially, if we think about the demographic equation expressed here, when we're producing an estimate of the population between two censuses, for example, then we have estimates of actual events for births, deaths, and in and out migration. Whereas when we're using this formula in the context of producing a projection, our quantities of births, deaths, and migration are based upon assumptions we might make about future demographic events. So this graph gives a visual illustration of the cohort component methodology. So we start off in the top left with a population pyramid at time t. So for this methodology, we need detail of population, a base population, with both detailed age and sex information. So we take this population pyramid and we age it on. So we move each of the bars of our population pyramid up by 1 year or one age interval. So this gives us what we call the initial population. So that initial population wouldn't be a good projection, just this aging on process, because we haven't taken into account our components of change. So we need to add in any births that occur. We need to take away deaths, and those deaths will follow a strong age pattern. So we'd expect most of the deaths to be at the oldest ages. And just as we had population with age and sex detail, we need that detail in our components of change too. We need to add in migration and the age detail of that in migration, take away out migration to give our population at a time point in the future. The cohort component methodology can be carried out in different ways. It certainly requires age detail, but it can be carried out by single year of age or by grouped ages. If we are using 5-year age bands, then we will be producing projections 5 years on. So, for example, projecting the population between 2001 and 2006. So this requires us to have births, deaths, and migration data grouped by 5-year age bands. If we're working with annual projections, then we need a single year of age information for our base population and our components of change. And our projections are for intervals of individual years. So a single year of age model is useful in that it gives very versatile output, but it has a large increase in data requirements. The data might not be available, particularly for subnational populations, requiring us to estimate perhaps some of that missing detail in terms of age, individual year of age data. So if we're working with a population projection that uses 5-year age bands, the first process that we do for this is to age this population on. So here I have a population in 2001, 5-year age bands from 0 to 4 all the way up to a final age band of 90 plus. And to age that population on, I'm literally moving each population to the adjacent age band. So the 0 to 4 population, of whom there are 3,348 people, are moved in 2006 to the 5 to 9 age group. And this clearly requires me then to estimate the recorded male births, so this is for males, these particular population counts, for the period 2001-2006 to make up the 0 to 4-year-olds in 2006. And this gives us what we call the initial population. So as I mentioned earlier, the initial population is not the final estimate because we have an assumption here that everybody has survived. So we need to use recorded deaths by age in 2001 to 2006 to adjust each age group for mortality. So some of the 0 to 4-year-olds in 2001 won't make it to 2006 due to mortality. We need to take that into account. And similarly, we need to adjust for migration. So some of those 0 to 4-year-olds will move away from an area, but equally some will move in to an area. So we need to take into account of each of these components of change to give our estimate of the male population in 2006. If we're thinking about projecting into the future, we have a similar operationalization of the demographic equation. But when we project into the future, we have to make assumptions about what is going to happen to fertility, mortality, and migration, because we don't have actual counts of these things that occur in the future. And what is typically done here is we use a set of assumed age-specific rates for fertility, mortality, and in and out migration. And we apply those to our population. And the particular rates we choose to use in our projections are based upon assumptions we make about the future. So we could assume that recent experience is held constant. So we could assume that the set of age-specific mortality rates that we observe in our most recent data stays the same for the duration of the projection period. Or we can continue past trends. So keeping with the theme of what we might assume around mortality, we might assume that the decline in mortality rates that we've seen over the past 100 years or decade continues into the future. And we might project that decline in mortality rates forwards. Or we could use particular targets. So we could assume that fertility is increasing and it will increase until it reaches replacement level. So for replacement level, we'll be talking about a total fertility rate, which I defined in the first talk as being set at 2.1. Or we can produce a projection that seeks to understand the processes that cause change in population, particularly locally. If we know that there's going to be a local housing development, we might wish our projections to fill that housing development with people using a particular migration age set of age-specific rates. So there are 6 stages in running a projection using the cohort component methodology. We start off with our base population at the start of the period. We calculate the estimated births to that population over the period of the projection, and we usually use a set of assumed age-specific fertility rates, which we apply to our base population in order to do that. We then age on our base population, our existing population, adding in the births to the bottom, to provide an initial population. So this is the aged on population before we adjust for deaths and migration. The next step is to estimate those, the deaths and migration that occur over the first stage of our population projection. So we take a set of age-specific mortality rates and apply these to our initial population. And equally do the same with a set of age-specific in and out migration rates. And after we've added in the effect of in migration, taken away the effect of mortality and out migration, we generate our end population. A note of caution here. So far in all of the lectures or talks that I've gone through in this course, we have talked about annual rates, whether for fertility, mortality, or migration. So we might think about the annual death rate for 5 to 9-year-olds within 2009. But rates can, of course, be for longer periods. So we might use a 5-year death rate, and this is particularly useful if we're producing a 5-year population projection. So the 5-year death rate for 5 to 9-year-olds will be based on the deaths to that group over the next 5 years, over which time that population group would be aged between 10 and 14. So whenever you're given a set of rates for a projection, always check if they are annual or 5-year rates. If you're working with a projection that uses 5-year age bands, you need to have 5-year rates of mortality and migration. So stage 1, we're taking our age population, our base population at time point t with an assumed age and sex structure which we record in the data. Stage 2, stage 1, we're aging that population, starting with this base population, which will then age on in later steps. In stage 2, we're calculating the number of births that occur in a particular time period, t plus n. So we're multiplying our base population of each female age group by an assumed age-specific fertility rate to give the number of births for each age group of woman. And then we're summing the total births over that period and then applying a sex ratio to give us the distinction of male and female births. So we need this sex detail in our estimate of the number of births. And these represent the estimated initial population of the first age group at the end of our first time period. So here's an extract from an Excel sheet to show how these are calculated. So I have my female population with age detail, and I have the population at each age group. I have a set of 5-year fertility rates, and I can then multiply each of these age groups by the appropriate age-specific fertility rate. So here I'm including the 10 to 14 age group because I'm producing estimates of birth over a 5-year period. And some of the women in this age group will give birth over that 5-year period when they move to the age of 15 to 19. So by applying the age-specific fertility rates to the start population, I can get an estimate of births to females, and then these can be added together to give a total number of births. And then using a sex ratio of 0.51 of those births we might expect to be boys based on previous estimates and data. Slightly higher proportions of boys than girls tend to be born. We can then calculate the male births and the total number of female births. So we have 3,484 male births over this first time period. And we have 3,318 female births over this first time period. So we can now add those births into our initial population. So we have the 3,318 female births here, which gives us our initial population of 0 to 4 females. The rest of the start population we are aging on. So the 0 to 4 population, the start population is aged on by 5 years to reach the age of 5 to 9. Similarly, the 5 to 9 start population is aged on to give us our initial population at age 10 to 14. For the final age group in our initial population, we're adding together both the population who were aged 80 to 84 in our start population and the population who were aged 85 plus in our start population. So in the next step, we're applying our age-specific mortality rates to the initial population. So for each cohort of the initial population, we're multiplying these by the assumed age-specific mortality rate for the age at which they started the time period. So for the deaths within the first cohort age 0 to 4, we're multiplying by the new births for the mortality rate for newborn children. For deaths within the 5 to 9 cohort in our initial population, we're applying the age-specific mortality rate for the 0 to 4s in the start population. For the final cohort, our estimate of deaths is slightly different. We take our base start population for age 80 to 84 and multiply that by the age-specific mortality rate for that particular cohort. And we take our base start population for the 85 plus group and multiply that group by the age-specific mortality rate for that cohort. And we add these two things together. So here we see a diagram expressing what is done here. I have a set of age-specific mortality rates. Again, these are 5-year death rates. So our initial population at age 0 to 4, 3318, is multiplied by the age-specific mortality rate for newborns. Our initial population at age 5 to 9, 3659, is multiplied by the age-specific mortality rate for the 0 to 4 age group, which is the group they have passed through to be aged on to become this initial population. So that gives us our estimate of deaths. For the final two groups, we use the start population. So here at age 80 to 84, we're using the start population, which is 1162, multiplying that by the age-specific mortality rate, and summing the product of the start population at age 85 plus and the corresponding age-specific mortality rate to give us the number of deaths for this final age group of 85 plus that we can combine with our initial population, which is simply aging on the start population. We can do the same for age-specific migration rates, so exactly the same process as I've been through for mortality rates, except that here we're using age-specific in-migration rates with our initial population to calculate migrants for each age group. We can do the same for out-migration rates, apply those to the initial population to calculate our out-migrants for each group. And then we're ready for stage 6, where we can bring it all together to calculate our final projected population. So in stage 6, we're taking our initial population, we're taking away deaths, adding on in-migrants and taking away out-migrants to give us the our end population, or population at a later time point. So here we can see this in the screenshot from an Excel spreadsheet. At age 0 to 4, our initial population was 3318. We add on 1,632 in-migrants. We take away our estimate of out-migrants. We add in our deaths to give our forecasted population of 3,300. So a slight decline in population for compared to our start population of 3659. So that's the general approach to producing a population projection using the cohort component methodology. But of course, there are a whole set of other strategies and choices that we might make. A key area to mention is the use of variant projections. So variant projections are really essential to allow us to explore change in population under different and plausible scenarios. So we can look at different scenarios, such as scenarios where past trends in fertility, mortality, and migration can continue. And we can inform those trends according to short and long-term analysis. We can assume present rates will remain unchanged. We might assume that fertility rates will continue to fall, but will level out at a particular level of fertility, or after a certain number of years. We can assume that things we observe in society, such as postponement of first birth to later ages, continues or not. Or we can make our projections respond to things like expansion of house building that might increase rates of in-migration, or closure of businesses that are anticipated that might lead to increases in rates of out-migration, and many other different options. A set of official population projections are produced in the UK. These were originally produced nationally by the Government Actuarial Department. However, from 2008, responsibility is transferred to the National Statistical Agencies, to the Office for National Statistics in England and National Records of Scotland in Scotland. National projections are produced by age and sex and prepared every second year. But subnational projections are also produced by statistical officers of the 4 countries in England, Wales, Scotland and Northern Ireland. And Scotland are now have produced a set of experimental projections within what they call council areas. So looking at projections for areas within councils of Scotland, and the following training in POP group culminates in replicating those projections for sub-council areas. The most recent national Population projections are updated regularly, so we now actually have more recent population projections than indicated by this slide, which is suggesting 2014 was the latest. The main focus of these projections is on the first 25 years. So we have, but it is possible to get longer term projections which consider a longer period of projection than 25 years. National statistical agencies tend to produce a principal projection, and this is based on an assumption of what is considered the most likely patterns of fertility, mortality and migration in the future. But there is clearly uncertainty in all projections, and for this reason all of the national statistical agencies, including the Office for National Statistics, produce a series of variant projections based on alternative but plausible assumptions about fertility, mortality and migration. So here is a graph indicating a set of variant projections. These are taken from the Office for National Statistics 2010 based national projections, so quite a dated set now. But the value of the slide is indicating the variability in the projections under different scenarios. So the top line here, indicated HP, is indicating how population would change between 2011 and 2081 under a scenario of high fertility, high life expectancy and high migration. So we see a much larger population under this assumption, because this assumption is assuming there'll be more babies born, more people will survive to the oldest ages, and there will be high levels of migration, so new populations moving into the country. So under this scenario in 2081, the population of the UK is projected to be around 115 million. Whereas the LP projection, this is showing a set of assumptions that predict low fertility, low life expectancy and low migration. And under this projection, we see very little increase in the population of the UK, so remaining just under 70 million between 2011 and 2081. So quite a large area of uncertainty if we use different but perhaps plausible assumptions of fertility, mortality and migration, and one can see the principal projection somewhere in the middle, projecting an increase from around 70 million in 2020 to around 90 million in 2081. One question we might ask is, how well do these projections match reality? So this graph, these sets of graphs show the actual and projected life expectancy at birth for males for various different projections, going from the 1971 based projections, which you can see here, all the way up to the 2004 based projections. The black line here is showing the actual change in life expectancy over this period. So we can look at how some of these assumptions match reality. So we have this graph here for males, but also for females. Similar results in each, so I'll just focus on males. But the key point to note here is that the change in life expectancy that was projected at each of these time points in the 1970s and in the 1980s actually underestimated the improvement in life expectancy that we saw in reality. So if we can assess how well our projections do as the data becomes available, and one thing that appears to have happened with mortality is the improvements in mortality during the 1970s and 1980s was lower than that which actually occurred. So a nice reference if you want to look at it by Shaw, 50 years of UK national population projections, how accurate have they been? And that's in population trends. So we're not just interested in how populations change, we're also interested in how population age structure changes. Very important for service provision and very important for the impact on our components of change, fertility, mortality and migration, which follow age patterns. Here we can see that the change in the population age structure of the UK, according to those 2010 based projections, And the general finding here is an increase in population. So the lines here show the population pyramid in 2035, and the population pyramid here is the population structure in 2010. We see a general growth in population across all ages, but perhaps particularly at the older ages. So we see population aging here. An increasingly elderly population structure in the UK is anticipated in the future, partly due to people living longer, partly due to a decline in fertility, so fewer births, but also due to demographic momentum. So the moves of these larger cohorts who were born following the Second World War, moving into the older ages. If we think about uncertainty in projection, there are a number of things that can be taken as a rule of thumb. First, that uncertainty increases with the duration of the projection. We know from the migration talk that error or uncertainty is likely to be greatest for the migration component. We see error to increase for smaller areas. So as we move from national projections to subnational, district or council area projections, to local projections within those council areas or district areas, we would see an increase in error as we move to smaller areas. And if we're thinking about age, we tend to see the largest errors for the very old and the very young. Uncertainty is often handled using these variant projections, which use different but plausible assumptions on each of our components of change. So just to finish off with a summary, population projections are very important for planning. They allow us to inform decisions around things like school places, housing developments, provision of care for older people, and so